Hi there. In today's lecture, we're going to be going over some of the rules for derivatives and several examples on the chain rule, which can get quite complicated. Okay, so the other rules for derivatives are a bit simpler, and they will be covered in the tutorial. Okay, so please make sure you go through that. Okay, we'll start off with the definition for the derivative, which you've seen before. So what we do is we take the average gradient between 2 points. So here we have 1 point at x and another one a little bit away at x plus h. So the average gradient, let's call that m, is going to be f at x plus h. So that's our y2 value minus f at x, that's our y1 value, over x plus h, that's our x2 value, minus x, that's like our x1 value. We can simplify this a bit, so we get f of x plus h minus f of x over h. Okay, so that's for the average gradient between those 2 points. To find the gradient at a single point, what we do is we take this h value and make it go to 0. So in the limit, these 2 points coincide, and the average gradient between 2 points becomes the instantaneous gradient at a single point, and we call that f prime. Okay, so then that will be the limit as h goes to 0 of our average gradient that we have above. So f of x plus h minus f of x over h. Okay, so that is the definition of the derivative, and given some function f, in principle, we could find the derivative using this definition. Okay, so given a function f, we can find the derivative using this definition. Okay. However, some functions are quite complicated, and using this definition will therefore be complicated as well. So what we do is we use this definition to come up with a set of rules, and then we use those rules to find derivatives. Okay, so instead of using the definition as is, we use the rules instead. Okay, and there's a few rules. You should have seen them before, but let's just do a quick recap of them. So the first one is the power rule, and that helps us a lot when it comes to dealing with polynomials. So the derivative of x to the n will be n x to the n minus 1. Okay, so you should have seen that before. Then we have d by dx of k times f of x is equal to k times df by dx. So constants, those are not affected. We can simply take them out of the derivative operation there. And together with this, we have d by dx of f of x plus or minus g of x is equal to df by dx plus or minus dg by dx. Okay, so the derivative of the sum is the sum of the derivative. And then rule 2 and rule 3, we commonly combine those two, and we say that derivative, or the derivative operation, is linear. Okay, so you might see this later on. So whenever something is linear, it behaves in this fashion. So constants can be taken out, and we can distribute over sums like that. Okay, number 4, we have something for the product. So if we have the derivative of f times g, we alternate the derivative. So we apply the derivative to the first term, so apply it to f. We leave the second function alone, plus we leave the first function alone, and then apply the derivative to the second. Okay. And this extends naturally to higher order products. So just as a note, if we have d by dx of f of x times g of x times h of x, then we have the same sort of alternating behavior. So we take the derivative of the first one, and then we leave the others alone. So we have g times h plus, then we apply the derivative to the second, leaving the others alone. So we have f dg by dx, we leave h alone. And finally, the last one gets to have the derivative, so it will be f g dh by dx. Okay, and then I'll leave this as a homework exercise to prove. Okay, so you can have a think about how you would prove this for 3 functions, and maybe you can prove it using n functions. Okay, but 3 functions, that should be enough for now. Okay, number 5. Okay, the one that we're going to be using quite often, that's the chain rule, and then we have one more, which is the quotient rule. Okay, so the chain rule, if we have d by dx of f of g, okay, so we have this combination here where it's f of g, so they're composed with each other. When we're taking the derivative, we need to imagine ignoring the inside function, so ignoring g, and just taking the derivative of the outside part. So we ignore g, take the derivative of f, so let's write that as f prime. So a different notation means the same thing. We leave the inside parts alone. Then we multiply by the derivative of the inside parts, so then times by g prime. Okay, so here we just have a single inside function, so we just have this single product between these two. If we had more compositions, then we would have more products being added on. So just as a little extension, if we had d by dx of f of g of h, something like that, so we have 3 compositions there, then we have the same idea. We look at the outside function, which is f, we differentiate that, and then the inside stays the same, so that's g of h, one more, times, and then we differentiate the inside part, but the inside part is just a composition of functions like we had before, so we can just apply that rule. So then this will be g prime of h of x times h prime of x. Okay, very similar to what we have in the previous line. Okay, and then again, this naturally extends to as many inclusions that's given. Okay, so we can have f of g of h of k, and so on. We simply repeat this process. Okay, and then lastly, we have the quotient rule. So d by dx of f over g. So if we have a quotient of functions, this is going to be given by f prime g minus f g prime. So very similar to the product rule, but we've got a minus, and also we need to divide by g squared. Okay, so that is the quotient rule. Now, you could just remember this as the quotient rule, but if you do forget it, we could also rederive the quotient rule using the chain rule and the product rule. So, in case you forget, okay, what we can do is, instead of writing it as a quotient, we can write it as d by dx of f of x times g of x to the minus 1. So having g to the minus 1 is the same as having it in the denominator, which is exactly what we have there for number 6. We've got g in the denominator. So now, notice we've got a product of two functions, so we can use the product rule. So this means we differentiate the first one and leave the second one alone. Okay, so we have f prime times g inverse, not inverse, just exponent minus 1. So just while we're on that, remember that there is a difference between g inverse, so this is not the same as g of x. Let's put brackets around minus 1. Okay, so just because the exponent is minus 1 doesn't make it an inverse. Okay, so inverse, we write the exponent minus 1 on the function like this. We have on the left-hand side, that's an inverse function. Okay, we know how that works. On the right, that exponent there is just saying that the function belongs in the denominator. Okay, so please don't mix those up. Okay, especially in the next section where we look at inverses and derivatives of inverses, please don't mix up the two notations there. Okay, then plus, we leave the first function alone, and then we differentiate the second. But as we have there with the warning, it's g of x to the minus 1, so we've got an outside function, okay, something to the power minus 1, and we have an inside function, which is g of x. So we need to use the chain rule. So this is going to be times by minus g of x, and let's put that in brackets so we don't mix anything up, to the minus 2, so that's just using the chain rule. Then the derivative of the inside part, that's going to be g prime. Okay, so we can simplify this a little bit. Here we have f prime of x over g of x. Remember that minus 1 in the exponent means it belongs in the denominator. Then we have a minus from when we did the chain rule. We're going to have f of x times g prime. And again, that minus 2 in the exponent means it belongs in the denominator. Okay, so in the first term, we have a g in the denominator. In the second term, we have a g squared. So we can find a common denominator and add the two fractions, or in this case, subtract them. So for the first fraction, we can multiply top and bottom by g of x. So we're going to have f prime of x, g of x, minus f of x, g prime of x, all over g of x squared. Okay, which is the quotient rule that we had above. So if you ever forget the quotient rule and you remember the product rule and the chain rule, then you can rederive it. Okay. So that's something good to keep in mind. Okay, let's have a look at some examples using this chain rule, product rule, and so on, and see how we calculate these derivatives. Okay, so examples. Number 1, we have y is equal to sine of x squared. Okay, so we'll go through this slowly at first. So here we've got this outside function, sine. Okay, that's the outermost function we can see. And we've got this inside function, x squared. Okay, so it's literally inside that other function. Okay, it's the argument of the function. So when we are applying the chain rule, when we're taking the derivative, we need to take the derivative of sine first, and then multiply it by the derivative of x squared. Okay, so differentiate the outside function, leave the inside part alone, multiplied by the derivative of the inside function. Okay, so that's what we need to do. Let's do that. So y prime is going to be the derivative of the outside function. That's going to be cos. So it will be cos x squared remember, we leave the inside part alone, times the derivative of the inside part, that's going to be 2x. Okay, and we can stop there. Okay, so that's the first example. Number 2, something a bit more complicated. We have x squared plus 1 cubed, x squared plus 2 to the 6. Okay, so we've got a combination of products and chain rule. So we have something cubed, that's the first part. We need to use the chain rule because we have an outside function as well as an inside function. And it's also being multiplied by something else, which also has an outside function and inside function. So we're going to have to use the product rule and the chain rule. But let's not do everything at once. Let's take it step by step. So y prime, we take the derivative of the first term, leave the second term alone. So that's going to be d by dx of x squared plus 1 cubed. Let's put that in brackets. So that's our first part, and the second part stays the same. Plus, now we leave the first part the same, so that stays like that. And then we take the derivative of the second part. Okay, so step by step. So, when we want to take the derivative of this first part, we need to use the chain rule. So, outside function, that's something cubed. We're going to take the 3 down, turn that into a 2, and then take the derivative of the inside. So, that will be 3 x squared plus 1 squared times, and then the derivative of the inside, that's just going to be 2x. Okay, and then the other term stays the same. Okay, plus, and then for the second term in the sum, that x squared plus 1 cubed, that's going to stay the same. Okay, but now we have to take the derivative of x squared plus 2 to the 6. So the 6 comes down, the inside part stays the same, that becomes a 5. Then we take the derivative of the inside, and that will be 2x. Okay, so just a note on presenting your answer. So here we could do further simplification. So the 3 and the 2x we could multiply, the 6 and the 2x we could multiply. However, this is fine as is, but maybe if there are follow-up questions, maybe it would be better to simplify your answer. Okay, but if a question just states find the derivative, then this is perfectly acceptable. Okay, but maybe it would be better for you to simplify if there's more questions later on. Okay, so that just depends on what you're working with. Okay, let's look at example number 3. So we have y is equal to 1 plus 2x over 1 minus 2x cubed. Okay, so right away we can see that on the outside we have something cubed. So we're going to have to use the chain rule for that. And then on the inside, we have some function divided by some other function. So outside, we need to use the chain rule. On the inside, we're going to have to use the quotient rule. Sorry. Okay, so chain rule first, and then quotient rule second. So let's do this step by step. So y prime, that's going to be d by dx of all of this. 1 plus 2x over 1 minus 2x, all of that cubed. Okay, so first, let's do the chain rule with the outside part. So y prime will be 3, 1 plus 2x over 1 minus 2x squared, and then d by dx of the inside part, 1 plus 2x over 1 minus 2x. Okay, so I'm breaking it up over multiple lines, just so that it's not too overwhelming or messy. Okay, if you try to do everything on one line, you might lose track of what you're trying to do. Then it just becomes overwhelming, and it makes room for errors. Okay, so we don't want that, so take your time, do it over multiple lines if you need to. Just make sure that each line is correct as you're going through it. Okay, so no need to rush and put everything down at once. Okay, so y prime, that's going to be 3, 1 plus 2x over 1 minus 2x squared, so that part stays the same. And now we just need to use the quotient rule. So remember what that was. Let's just write it on the side. F prime g minus fg prime all over g squared. Okay, so f prime, so that's the derivative of the top, that's just going to be a 2. Then g, that's just going to be 1 minus 2x, minus f, that's going to be 1 plus 2x, g prime, that's going to be minus 2, all over g squared, so that's 1 minus 2x squared. Now again, this is perfectly fine as is. You're free to simplify if you want to, and again, maybe if there's follow-up questions, it would be better to simplify. For example, if you needed to calculate the second derivative, maybe it would be better to work with something that's been simplified. Okay, but again, if this is the only question, right, just find the first derivative, then this is perfectly fine. Okay, I'm not too worried if you are simplifying further. Okay, so that's going to be it for this lecture. So just a brief recap of the different rules. In the next lecture, we're going to be looking at implicit differentiation. Okay, so that's when we write something of this form. So implicit differentiation. Okay, so that's if we have something like x squared plus y squared is equal to 1, and we want to find y prime. Now, just by looking at this, it's not too clear what is a function of what. So x could be a function of y could be a function of x, we don't really know. So, in fact, the functional form is implied. So we just assume that y is a function of x, and since we have y squared, we have a function in another function, right? Because y is a function, and then it's being squared, that's another function. So we're going to have to use the chain rule. Okay, so when we are doing implicit differentiation, we need to be careful that this y squared is not treated the same as x squared. It's not a variable on its own. It is, in fact, a function of x, and we need to treat it like that. Okay, so it can get a bit complicated, but we'll go through it step by step. And then the main reason for looking at implicit differentiation, which we will do later in the next lecture, is finding derivatives. Derivatives of inverse functions. So that is when we have y is equal to f inverse of x. Okay, so sometimes the inverse function can be a bit complicated. You may have not worked with it so much. How do we find the derivative of such functions? For example, sine inverse or arcsine or cos inverse, the natural log, and so on. How do we find the derivative of those functions? Okay, but we will save that for the next lecture. If you have any questions on this or questions about anything else for the semester, please don't hesitate to email me. Okay, so you can email me whenever you want, and I will try to get back to you as soon as possible.